Нормально? Спасибо. И в конце нужно что-то нажать? Нет?
Ну вот обычно как
на стоп.
Красное, да, но она не горит, поэтому да, на стоп.
Ага. Вот только на стоп записи, да?
Да.
Или на оба? На оба. Хорошо. Угу. Спасибо. Okay, so last time we discussed the algebra. Probably it was script R, yeah, the sum over n k groups of representations of G, L, N, F, Q with multiplication given by parabolic induction. So at the level of representations, or the same as Philip Hall multiplication at the level of class functions the same as isomorphism classes of representations of Laurent polynomials. Okay, and then so on the one hand, well, maybe it will be clear afterwards, or already follows essentially from what I said about induction of Caspar representations. So essentially, this will be isomorphic to the direct sum over all Caspar representations. Just copies of this archetypical ring lambda, but with coefficients in well, how to say, lambda tensor z of q. Okay, and if this Caspar representation is just trivial representation of GL1, so many copies of this. The copy of lambda tensor z of q, tensor over z. So it extends scalars corresponding to the trivial Caspar representation of GL1 is the subalgebra of class functions supported on the unipotent elements. And unipotent is the same as nilpotent. Namely, u here equals 1 plus x there. Okay, and now for a few next classes, we will study this copy. So this is called the Philip Hall algebra. Okay, so let me define it formally once again. So we consider the ring O, and O is either FQ formal power Taylor series of parameter T, or it could be the ring of integers of a finite local field of characteristic 0. Sorry, finite extension of QP. So, well, it lies in something, well, maybe let me call it Q, Gothic P, and then we have the corresponding extension of integers, p-adic integers in a certain finite extension. So if, so to say, Q is P, hence O is just ZP. Well, okay, now this ring O has a unique maximal ideal. And the quotient is the residue field. Okay, now the Jordan normal form, or the classification of finite abelian groups implies that any O module, well, finite O module M is isomorphic to a direct sum of cyclic modules, to the power lambda I, and this will be denoted M sub lambda. And so the isomorphism classes of finite O modules are in natural bijection with partitions. Okay, now given a module, how to see what is its type, lambda? Well, for the transposed partition, its ith component will be equal to the dimension over the residue field of the maximal ideal to the power I minus 1 over the maximal ideal to the power I times M. Okay, and I hope you know this from some basic algebra classes. Okay, now M is cyclic if lambda is just one part partition. And M is elementary if it is annihilated by the maximal ideal. In other words, it's just a vector space over the residue field. So it implies that the corresponding partition is just a sequence of ones. Now, the important thing is the duality. This duality, well, it's important in many respects. For example, it is similar to the Gelfand trick we discussed some couple of months ago. It will imply that the whole algebra is commutative. I always write Philip Hall just because there is another Marshall Hall, well-known combinatorist. And by the way, I'm following the book by Ian Grant MacDonald, Symmetric Functions, and Hall Littlewood. I forgot. Probably Hall Littlewood. Polynomials. Maybe there is no Littlewood, I forgot. I think it's chapter 2 that I'm following, or part 2. Okay, so the duality is M goes to M dual, which is just Hall. Okay, thank you. Hall, thank you. Home from over O, from M to a certain dualizing module E. And now this E is a dual of O itself. Now O is the inverse limit of over O modulo the powers of m to the power I. Yeah, this is just sort of definition. But, well, there are natural projections. O modulo m to the power I plus 1 projects onto O modulo m to the power I. This is clear. But, in fact, there is also an embedding in the opposite direction. Yeah, for example, Z modulo 5Z is embedded into Z modulo 25Z, right? Just multiplication by P. Well, there is a generator of M. I don't know how to. Of M. Well, I don't know. Well, it's clear. Sorry. Okay, so we can consider the colimit with respect to these embeddings. Okay, and for example, if O is the formal series, then what is E? Didn't you discuss something like this with respect to Fourier transform? Because Fourier transform generally is defined on locally compact abelian groups And then there is a notion of Pontryagin duality, and Fourier transform goes from group to dual group. And then the role of E is played by the circle for an abelian group A. This dual is just the homomorphisms from A to the circle. I mean, continuous homomorphisms. And it also works literally as stated here. So what is the dual to this locally compact abelian group? See, the Fourier transform, like R is self-dual, yeah? Then what is dual to Z? Yes, S1, certainly. And the dual to the circle is Z. That's clear. And somehow this exact sequence, 0, Z, R, S1, 0, is self-dual. Okay. Now, every local field is self-dual. For example, R. But also, the Laurent series with finite coefficients is self-dual. Well, so the quotient will be dual to that. Well, let me write like this. Okay, so this is E. This is O. And this is self-dual. By the way, what is the duality? If it's self-dual, you should have perfect bilinear form. What is the pairing? Maybe it's easier to assume that Q is a prime number. At least Shuai and Divan, who were attending the periodic class last fall, must know this. Well, the pairing is well, F and G is the, well, first of all, we take the residue at 0 of F dg, or maybe this way the constants will, yeah, maybe they do not need dg, the constants will be in the kernel this way, yeah. Maybe let me write fg dt, something like this. Okay, this will be just an element of the field fp, right? And then just take the exponent of this thing, and it will lie in the circle. Or maybe, I should say, whatever, 2 pi I don't know, if you wish. But, I mean, embed the additive group of the finite field into the circle. Maybe over P. Okay. Now, if Q is not P, then it's composed with trace from FQ to FP. And if your field is p-adic numbers, then do it yourself. Or recall what I explained half a year ago. Okay. So, once again, it is just the quotient of a Laurent series modulo Taylor series. or else Q P over Z P. Okay, so this is the duality, and well, again, just take any cyclic module and take its dual. It will be the same. Well, also a cyclic module isomorphic to this one. So non-canonically, for any M, non-canonically, M is isomorphic to its dual. Like any finite abelian group is non-canonically isomorphic to its Pantryagin dual. Yeah? But it's only true for finite groups, as you see. In general, certainly it's wrong. Okay. Now, what else terminology do we need? For an element of a module, there is a notion of height. H of x is R if the maximal ideal to the power R annihilates x, but this is the smallest power that annihilates x. Okay, now M sub R inside M is the set of all elements whose height is at most R. So this is the annihilator in M of the rth power of maximal ideal. Okay, and now let's perform the first computation. So also set phi m of t is just the product 1 minus t, 1 minus t squared, so on, 1 minus t to the m. So it's sort of a t analog of m factorial. And then our first lemma says that if we consider the group of automorphisms of m lambda, then, well, it's a finite module. Its automorphisms form a finite group. And well, it's sort of analog of GGL, but some not over a field, but over a ring. Yeah, like we consider GGL of Z modulo 4Z. Yeah, it's something of this form. It is a lambda of Q, certain polynomial. So it's Q to the power total weight of lambda plus twice n of lambda, and the product over all positive I, phi mi of Q inverse, where lambda is written in this form. And well, n of lambda, as I said before, is the sum of I minus 1 lambda I, or else the sum of lambda I transposed choose 2. Okay. So let's prove this. well, first of all, most simple-mindedly and straightforwardly, the automorphisms of M lambda, well, so M lambda is the direct sum of such guys. And each such guy has a generator. It's a cyclic submodule has a generator. And now we just have to choose similar generators. Okay? And send the standard ones to those similar. So it's the number of collections of x1 and so on, x r, such that the height of xi is lambda I, and the whole model M is just the direct sum of submodules generated by those elements. Okay, so we now have to find describe all the collections of those x1 and xr and number them. So let n in M be a submodule generated by some elements of height at least r, and let x be any element of M. Then I claim the following are equivalent. And then using those equivalent properties, we will recursively construct such sequences. Starting from the maximal height on. So the first property is that the height of x is exactly r, and the intersection of submodel generated by x with n is nothing. And the second property is that x lies in mr, so has the height not more than r, and it does not lie in r minus 1. That's good. It means it has exactly height r. But you also allow to add n sub r. So these two are equivalent. And what is even better, the number of such x's is q maybe to the power lambda 1 transposed plus so on plus lambda r transposed times 1 minus q to nu r transposed minus lambda r transposed, where nu is the type of our model n. Okay, maybe let us name this statement. So let's prove this. A implies that X lies in MR. That's clear. Now, if X lies in MR minus 1 plus NR, then when we multiply X by the R minus first power of the maximal ideal, we have not zero, but it lies in NR, well, inside N. And it implies that the cyclic submodel generated by X has non-trivial intersection with N. That's a contradiction. Now, conversely, B implies that the height of X is exactly R. And now, if the intersection of the cyclic submodel generated by X with N is non-trivial, then when we multiply the maximal ideal to some power M with X, we land into N for some M that is strictly less than R. And hence, we see that when we multiply X by the R minus first power of maximal ideal, then it lies in the so-called N1 in N. Okay, but N is generated by elements of a height at least R. So the maximal ideal times R minus 1. Sorry, the R minus first power of X, of maximal ideal times X, is equal to the maximal, the R minus first power of maximal ideals times Y for some Y in our submodule N. So it implies that the difference X minus I is annihilated by R minus first power, so lies in R minus 1, and hence X lies in M R minus 1 plus N intersected with MR, which is the contradiction, right? Okay, so we proved the equivalence of A and B, and now we have to count. Let's count. We have M modulo MR is isomorphic to the rth power of maximal ideal times M, just by multiplication, yeah, because multiplication will kill exactly this. And hence the length of MR is the length of M minus the length of maximal ideal to the power R times M, and this is equal to the sum from I equals 1 to R, the length of M to the power I minus 1 M modulo M to the power I M, and this is equal by what I erased on this blackboard, lambda 1 transposed plus so on plus lambda r transposed. Also, we know that the length of m r minus 1 plus n is equal to the length of m r minus 1 plus the length of the sum m r minus 1 plus nr modulo m r minus 1. Okay, so this is the length of m r minus 1 plus the length of nr modulo n r minus 1. Okay, and then this is lambda 1 transposed plus so on plus lambda r minus 1 transposed plus nu r transposed. Okay. Now we're almost done. Yes, hopefully. Sorry. But certainly a real mathematician should have answered, yes, it is, to your question, and continue with his lecture. Okay, so this is it, and now we're done because it implies that the order of the automorphism group of M is the product of such things. Well, maybe R, I should say. R over R equals lambda 1 and so on, lambda k minus 1 over all so on, taking nu equals lambda 1 and so on, lambda k minus 1 for R equals lambda k. Okay, and now it remains to check that it is equal to a lambda of q, and maybe let me stop here. So let me leave this as an exercise. So maybe I'll, I don't know, I can write it, include it in the home assignment, but in April, so it makes not much sense. I don't know, but maybe I will. Okay. So we computed the order of orthomorphism group. In particular, you may try and check that it gives the correct order of SL of Z modulo for Z, which should be, well, GL rather, GL. So what should it be? For SL it's 48, and for GL, I guess it should be 96. Maybe let's try. So our lambda is what? Yes, I think it's just 2. So O is well, Z 2, and lambda is just 2, right? So what do we get? 2 to the power 2 plus what is n of lambda? Yeah. So plus 4. Yes. And then there is only m2, and it is equal to 1. So 1 minus 1 minus 1/2, yeah? Right? Pardon me? GL2, sorry, GL2. Yes, GL2. So our partition is 2, 2. Right? Yeah, so everything was wrong. Let's write down again. So what is 2 to the power 4? Now what is n of lambda now? For 2, 2. Huh? Okay, so 4 plus 4. Okay, and now what is mi now? Mi is, so m2 is 2. Okay, so we get 1 minus 1/2 times 1 minus 1/4, right? And what is this? So it is 1/2 times 3 over 4, and here 2 to the power 8. No.
I'm not sure whether it is right.
Why?
Lambda is 2 times.
Yes.
So I think we need only 1. Okay.
No, I think it's okay. And so what do we get? To the power 8, here 2 to the 5th times 3, and it is correct. It is 96. So you see, how is it called? In USSR it was called Nauka Praktike, but now I don't know how it should be called. Okay, so now the whole algebra. Well, it has Z algebra. Well, it's a ring, so to say. Ring with a Z basis, so the free Z module, given by partitions. That is isomorphism classes of finite O modules. Okay, and now if I want to multiply two modules, m lambda times m mu, then I get the sum over all nu, m nu with certain coefficients. The coefficients will be called g mu, g lambda mu, or maybe one moment, sorry. Maybe let me write it this way. Mu times nu, it will be lambda, then lambda, mu nu. And now these coefficients, g lambda mu nu, is the number of submodules. Pardon me. Here over lambda. Yes, thank you. Thank you. Submodules in m lambda, isomorphic to m nu, such that the quotient is isomorphic to m mu. Okay. Pardon me? So is this algebra commutative? That's what you ask. We'll see momentarily. But first of all, we should worry if it is associative. And it is. So more generally, g lambda mu first and so on, mu rth is the number of flags m lambda is m, 0 contains, maybe 0 here, contains m1, contains m2, and so on, contains m r equals 0, such that the type of the quotient mi minus 1 over mi is isomorphic to mu I. Well, type. Okay. So it is associative. I mean, if you perform a few multiplications, you just have the structure constants equal to the number of those flags. And now, as Irina noted, well, position. This whole algebra, maybe I should call it H. H is commutative. Just because we have this duality. Okay, and the duality, if we had the exact sequence 0, what was it? Nu, m lambda, m mu, 0, then we just dualize, and we get 0 to m mu dual to m lambda dual to m mu dual to 0, but they're all isomorphic to things without checks. Okay. Now maybe as an exercise, let's compute some baby version. Just FQ modules. Just FQ vector spaces. Okay, so then they're numbered just by numbers, by dimensions. Like E n is the class of FQ to the power n. And En times E say, k will be what? At least proportional to what? Yes. Yes. And what is the coefficient of proportionality? Yes. So you take you take the Grassmannian of say k-dimensional subspaces in k plus n dimensional space over FQ. Well, I don't know how to write it over FQ. And this is the coefficient. Okay, and now what is this cardinality? Pardon me? Times? Maybe choose. How do you mean by times? Maybe you're speaking of dimension. I don't know. I ask about the number of elements, number of subspaces. So what is it equal to? Yeah. Yes. Yes.
Q in the power of a minus q in the power of k, and k goes, well, not k sum s, and s should go from 1 to k minus 1.
Well, so the answer will be, I luckily didn't erase this, so it's phi k plus n of q, right, over phi k of q times phi n of q. And this is denoted by k plus n, choose n, but q analog. Okay, and does everybody know why this is so? Vanya? Do you know how to count the number of points in Grassmannian? You do. And Sinuhe, do you? Everybody knows. Very good. Fine. So, in other words, you may say that En is the nth power of E1, but divided power. Meaning that you take E1 to the power n, but divided by this Q analog of n factorial. And say over rational numbers, this is just polynomial algebra in one variable. But over integers, by no means. It needs infinitely many generators. It's infinitely generated over integers. And the same will hold for our real Philip Hall algebra. It will be infinitely generated. But this time over integers and over rational numbers. In fact, it will be isomorphic to our celebrated ring lambda, but with coefficients extended from Z to polynomials in Q. So, well, we denote U lambda is the class of M lambda. And so these G are structure constants in this basis. And now the next proposition is that H is generated by the algebraically independent elements VR that are just U1 to the power R. Okay, so in each dimension, so we are speaking of just nilpotent elements, right? If we are over the field, say if we are speaking of formal Taylor series, then the representations are just nilpotent elements and nilpotent endomorphisms of vector spaces, and this corresponds just to zero endomorphism of R-dimensional vector space. Okay, and I claim that those zero endomorphisms generate the whole algebra. Okay. Well. So let's define such elements not just for integers but for partitions, because whenever we have generators of the symmetric function ring, they give rise to the basis numbered by partitions. So this will be V lambda 1 transposed, V lambda 2 transposed, and so on, V lambda S transposed. And well, this is somehow expressed through this most natural basis, A lambda mu U mu. This is just definition of those coefficients. Now, A lambda mu, by the definition, is the number of flags such that the type of M is mu, and the type of the quotient associated graded is 1 to the power lambda I transposed. This is an elementary model corresponding to the zero null point endomorphism. Okay, now if A lambda mu is not zero, that is, such a flag exists, then the maximal ideal times mi minus first lies in mith, and then recursively we conclude that the ith power of maximal ideal times m lies in mith, and hence the length of the quotient is at least the length of m modulo mi. And this implies that the sum mu1 transposed plus so on plus mu I transposed is at least lambda 1 transposed plus so on plus lambda I transposed. So it implies that the transposed partition mu dominates the transposed partition lambda, and it implies that mu is less than or that mu is dominated by lambda. And furthermore, if mu happens to be equal to lambda, then there is a unique such flag, namely mi equals the ith power of maximal ideal applied to our module. So it implies that the matrix A lambda mu is strictly upper triangular, and hence u lambda can be expressed via v lambda. Okay. So it implies that our algebra is just a free polynomial algebra on the generators v1, v2, and so on, with a basis v sub lambda. In other words, our algebra is isomorphic to the lambda algebra, but the isomorphism written down in the basis of U lambda, in the natural basis, certainly depends on Q. Yes? Well, you see that the basis is given by partitions, and if there were some dependencies, it would be smaller. We know that it's a basis. So we started with linearly independent. We just defined H as having such a basis. So the corollary is that there is an isomorphism of algebras from H. Well, maybe I should write that this H depends on O. The dependence is rather slight, maybe only on Q, on the cardinality of the residue field, but still, it is isomorphic to lambda, namely V sub lambda. So V sub R goes to, I need this renormalization for some reason that will become clear afterwards, times the generators, the elementary symmetric polynomials, and then U lambda goes to something which is called Q to the power minus n of lambda, P lambda of Q. So maybe I should write lambda tensor Z of Q if you wish. Well, I don't know. No, maybe I should not. It is just a number. It is just an integer. Okay. Well, some integer depending on Q. Right. And this is our next project. Sorry. Right. How should I say this? Right. So this. Okay. It lies in lambda. Okay. It is some symmetric polynomial, but it depends on Q. And sorry. Now it will turn out that this dependence on Q is polynomial. And this is sort of miracle. So the miraculous theorem, due to Philip Holm, is that there are polynomials G mu nu lambda of T with integral coefficients such that the structure constants mu nu lambda, well, for this algebra, so to say, of O, they are just the values of those polynomials at Q. So Q is the cardinality of O modular maximal ideal. So this is the first, maybe this is the first claim. The second claim is that the degree of this polynomial is at most n of lambda minus n of mu minus n of nu. And the leading coefficient, meaning at this, well, at t to this degree. Is the Littlewood-Richardson coefficient I mean that S lambda equals the sum of C lambda mu nu S lambda. Okay. Or in other words, if I take the irreducible representation V mu tensor V nu, and I induce from S m times S n to S m plus n. This is the direct sum of V lambda with multiplicity C to the power C V nu lambda. Okay. So somehow we fixed our local ring O, which had Q elements in the residue field, and we performed our study of the corresponding whole algebra. We obtained something, but then it turns out that this algebra depends very nicely polynomially on the whole family of local rings, just on the cardinality of the residue field, and it's a miracle. Like, well, we also observed it for the baby case. Yeah, then also this algebra whose structure constants were cardinalities of Grassmannians, they also behaved similarly. Yeah, we obtained some polynomials in Q. It's also sort of miracle. And what's the reason for that miracle? I guess you know. Pardon me? Right, absolutely, yes. So this polynomial in Q, maybe a polynomial in Q, since the Grassmannian is the union of some Schubert cells. In fact, these Schubert cells are also numbered by partitions. But this is a pure coincidence which does not have any meaning at this stage. Well, this Grassmannian, by some partitions, well, I don't know any other letters, maybe mu. And this mu is inscribed into n by k Young diagram. And then these are just cells, Schubert cells. And each cell is isomorphic to the affine space, just dimension. And so the number of elements in the corresponding Schubert cell is just Q to the power of number of boxes in this Young diagram. Okay? What exactly? What is this partition into cells? Well, can say this, but maybe I should rather compose some home assignment about this. So Schubert cells. We fix a flag, complete flag. So we start with our field. It doesn't matter what is the field. We start with, it doesn't matter, say k plus n. Let's note by r. K to the power r, k to the power n minus 1, and so on, complete flag. Okay, and now we consider k-dimensional subspaces. So subspace V, well, to dimension k, in here. So if we fix all the dimensions Vk intersect with k to the power s, then the set of such, well, of Vk's with such intersections is either empty, because you can say that, say, intersection with this is something and with this is even bigger, which makes no sense, or much smaller. It should be only one smaller at most by one. Is identical or isomorphic to some to something. And also, I should explain how all the realizable collections of dimensions correspond to the Young diagrams that are inscribed into this box, big box. Okay, so I will compose the home assignment about this, but this is some very basic fact of nature, that the Grassmannian is can be cut out into cells, and so then it's easy to count the points in Grassmannian. And we'll have to stop now, but the next time, and maybe in a week, we will essentially follow the same argument. So we needed to count the points in sort of Grassmannian. But now it's not just Grassmannian, but it's compatible with the structure of O modules, sort of O Grassmannian. But then again, we will prove that those O Grassmannians can be cut into cells. But the proof will be much more involved. It will take up 2 classes. And the corresponding, well, combinatorics requires many new names, at least, like arrays, or shapes, strict arrays, column strict, row strict, and so on. Okay, thank you.